por su presencia en las actividades del día de hoy. Les damos la bienvenida a la Universidad Nacional de Colombia, sede de Bogotá, y agradecemos su presencia en estas jornadas, las cuales sin duda constituyen un hecho histórico para nuestra institución, toda vez que contamos por primera vez, después de 60 años, con un ganador de medalla Fields, máximo galardón en el mundo de las matemáticas. Hacer una presentación de un Nobel de las matemáticas parece innecesario. Sin embargo, permítanos recordar algunos datos de la extensa y brillante vida académica del profesor Efim Zelmanov. El profesor Zelmanov obtuvo su PhD en matemáticas en la Universidad de Novosibirsk en el año de 1981 y el doctorado en ciencias, también conocido como doctorado de Estado, en la Universidad de Leningrado, hoy día Universidad de San Petersburgo, en 1985. En 1994 el profesor Zelmanov fue galardonado con la medalla Fields, recuerdo otra vez comúnmente conocida como el Premio Nobel de las Matemáticas. Esto fue principalmente por su solución al problema de Bohr-Seidel. El problema de Bohr-Seidel fue una conjetura que estuvo abierta por más de 90 años y muchos matemáticos notables del siglo XX intentaron resolverla. El profesor Zelmanov no solo resolvió este famoso problema, sino también muchas otras preguntas en el área de álgebra de Lie y álgebra de Jordan, problemas que estuvieron abiertos durante varios años.
Good morning, everyone. Welcome to the National University of Colombia in Bogotá. We appreciate your presence in today's academic activities, which undoubtedly constitute a historic event for our institution, since this is the first time, after 60 years, we have in our campus a winner of the Fields Medal, the world's highest award in the field of mathematics. It may seem unnecessary to introduce a Fields medalist. However, let us mention some of the myriad achievements during the long and outstanding career of the eminent Professor Efim Zelmanov. Professor Efim Zelmanov obtained his PhD at Novosibirsk State University in 1981 and the Doctor of Sciences degree at Leningrad State University, today St. Petersburg State University, in 1985. In 1994, Professor Zelmanov was awarded the Fields Medal, distinction commonly known as the Nobel Prize of Mathematics, for his Burnside problem solution. The Burnside problem was a conjecture that many notable mathematicians of the 20th century attempted to solve for about 90 years. Professor Zelmanov not only solved this famous centennial problem, but also solved many other questions in the area of Lie algebras and Jordan algebras, which had also remained unsolved for several years.
Bien, nos acompañan en la mesa el vicerrector académico de la Universidad Nacional, profesor Juan Manuel Tejero, el vicedecano académico de la Facultad de Ciencias, profesor Giovanni Garavito, el presidente de la Academia de Ciencias Exactas y Naturales, profesor Enrique Forero, agradecemos su presencia también, el director del Departamento de Matemáticas, profesor César Augusto Gómez Sierra, y el director del área curricular de matemáticas, el profesor Agustín Moreno Cañadas.
We are joined at the table by the Vice Chancellor of the National University of Colombia, Professor Juan Manuel Tejero, the Vice Dean of the Faculty of Science, Professor Giovanni Garavito, the Director of the Department of Mathematics, Professor César Augusto Gómez, the Director of the Mathematics Curricular Area, Professor Agustín Moreno Cañadas, and the Coordinator of the event, Professor Osvaldo Lezama.
Entonces, unas palabras de bienvenida de parte de nuestro vicedecano de Ciencias, profesor Giovanni Garavito. Muchísimas gracias.
Profesor Zelmanov, señor vicerrector académico de la Universidad Nacional de Colombia, estimados directores de departamento y de área curricular, de Matemáticas de la Facultad de Ciencias de la sede de Bogotá de la Universidad Nacional de Colombia, señor presidente de la Academia Colombiana de Ciencias, profesores del Departamento de Matemáticas y de la Facultad de Ciencias, estudiantes, amigos todos. Para la Universidad Nacional de Colombia y para la Facultad de Ciencias es un motivo de orgullo y de complacencia contar con la visita del profesor Zelmanov, medalla Field, en el campo de las matemáticas. Nuestro departamento de matemáticas podemos con orgullo decir que es la casa de los matemáticos en Colombia. Ha sido el lugar de formación de los profesores de matemáticas de muchas escuelas del país. Tiene un pregrado en matemáticas con acreditación de alta calidad y con reconocimiento tanto nacional como internacional. Cuenta con un doctorado en matemáticas y con varias maestrías. Profesor Zelmanov, le agradecemos que haya venido a Colombia y que esta sea la primera de muchas visitas de una relación muy fuerte que esperamos se establezca con la Facultad de Ciencias y con nuestro Departamento de Matemáticas. Bienvenido a su casa, profesor Zelmanov.
Well, thank you very much for your kind words. I'm very excited and honored to see so many of young people who came to listen to a mathematical lecture. Oh, thank you very much. The lecture will be on Lie algebras. I'm not 100% sure that everybody knows what a Lie algebra is. So I will say just a few words. In the second half of the 19th century, Sophus Lie introduced Lie groups, which is certainly one of the basic notions in mathematics. I guess you all know what's a group. And a Lie group is simultaneously a group and a manifold. So around at every point there are also coordinates. And so the multiplication of a group becomes a function in that coordinate. We can demand that that function is smooth or analytic, and then the object is called a Lie group. Lie groups arise everywhere, in algebra, in physics, in geometry. One of the most prominent physicists of Glashow once said that, I don't know if the God exists, but if he exists, he certainly knows about Lie groups. If you have a Lie group, then around the identity element, the multiplication in that group is determined by a certain class of algebras, Lie algebras. So these are very important algebras. What else should I say about them? If you do anything related to physics or any kind of mathematics, then it is better to know what are Lie groups and Lie algebras. Lie algebras and groups were classified by Killing and Cartan at the end of the 19th century, beginning of the 20th century. This is one of the peaks. It's a peak mathematics achievement. The classification came together with classification of root systems. These are basic symmetries that exist in the world. The same symmetries that are observed in elementary particles and in ornaments in Alhambra in Andalusia. But that's all about finite dimensional Lie algebras or groups. The interest in infinite dimensional Lie algebras appeared in the second half of the 20th century. It was largely due to strong connections with physics, conformal field theory. So, let us first talk about infinite dimensional Lie algebras. So we consider all Lie algebras over the field of complex numbers. Moreover, we consider graded Lie algebras. So our algebra is a direct sum of subspaces which are indexed by integers. And whenever you multiply two subspaces, their indices add. Well, and we assume that all these homogeneous subspaces Li are finite dimensional. Then, if we want to study infinite dimensional algebras, then it makes sense to start with those of them that grow not too fast. It's like with manifolds. The most interesting manifolds are those of small dimensions. So, we assume that there exists a polynomial which serves as a bound for dimensions of all these homogeneous components. That's a strong assumption, but a very reasonable one. The degree of this polynomial can be captured by this formula, which is called the Gelfand-Kirillov dimension of the algebra L. It appeared in the following way. If you have two finite dimensional, say finite groups, you can discuss which one of them has more elements. You can compare their orders. But what if both groups are infinite? That's how the notion of growth came into being. You can discuss which one of them grows faster. And the same with Lie algebras. If there are two infinite dimensional Lie algebras, you can discuss which of them grows faster. The growth is captured by this formula, Gelfand-Kirillov dimension. We also assume, if you want the classification, we assume that our Lie algebras are graded simple. Okay, they are allowed to contain ideals. You know that a simple algebra is the algebra that does not contain any ideals except 0 and the whole algebra. But these algebras are allowed to have ideals, but not graded ideals. So they are graded simple. Let's consider some examples. Let G be a finite dimensional, simple Lie algebra. So one of those objects that have been classified, I already mentioned it. And we consider Laurent polynomials over these algebras. This algebra of Laurent polynomials is graded by powers of the variable t. And the dimension of every component is the same, the dimension of G. So it's bounded, it's linear polynomial, and Gelfand-Kirillov dimension is 1. This is the so-called affine Katz-Moody algebras. Such algebras were introduced in the 60s independently by Victor Katz and Robert Moody, and they conquered the mathematical world. Another example, which is very close to the first one, slightly twisted version of it. We assume that our Lie algebra G is graded by a finite cyclic group, and we consider the following subalgebra of the algebra of all Laurent polynomials. Now, the series of Cartan-type algebras, they were discovered by Elie Cartan. Let us consider polynomials in n variables and all derivations of them. We know that derivations look in this way, the sum, some polynomial coefficients, and then partial derivatives. We define a grading. The degree of every variable ti is 1. The degree of every partial derivative is -1. Then the Lie algebra becomes graded. It starts with -1. And it is not difficult to show that the Gelfand-Kirillov dimension is equal to n. This algebra has well-known subalgebras, special, Hamiltonian, and contact, defined by certain differential forms, but I don't want to go into that. And finally, example number 6, the Centelis-Virasoro algebra. You take Laurent polynomials in one variable and all derivations. Here, it's a graded algebra. The dimension of every component is 1. So it's one of our examples. And it has a very interesting central extension. Well, this algebra has been discussed in mathematics for some time. And then physicist Virasoro also mentioned it. And somehow his name got attached to it. It's a counterexample to kind of a claim of Arnold that every concept is known by the second one who introduced it. It's not even second one. Now, so, I want to compare it with groups. There is a famous theorem of Gromov that classifies all groups of polynomial growth, and it turns out that there are very few of them. In algebras, the situation is opposite. The most interesting examples of Lie algebras that prove to be important in other areas of mathematics have polynomial growth and finite Gelfand-Kirillov dimension. In 1967, Katz decided to classify all graded simple Lie algebras of polynomial growth. And he was able to show that they are just all the examples above. But he had to impose one technical condition that ruled out the Virasoro algebra. So he conjectured that if the condition is dropped, then the only new algebra will be the Virasoro algebra, which was proved in 1991 by Olivier Mathieu. Extremely complicated proof. So now we can say that all graded simple Lie algebras of polynomial growth are just the examples above. Well, one can extend this setting a bit, and instead of Z-graded algebras, consider ZN-graded algebras, and then all the examples above will be modified. So the classification is still an open problem, but in a very particular case, when dimensions of all components are equal to 1, it was done recently by Eohara and Mathieu. Now, let's talk about superalgebras. A superalgebra is just an algebra which is graded by the cyclic group of order 2, period. So, it is a sum of two subspaces. One subspace is called even, it's A0. Another subspace is called odd. When you multiply two even elements, you get an even element. When you multiply an even times odd, it's odd. Odd times odd is even. That's it. Let's consider some examples. Let's consider matrices of size m plus n and divide them into blocks. Now, block diagonal matrices are even. Off-diagonal matrices are odd. That's it. Let's consider another example. The famous Grassmann or exterior algebra. It is presented by generators and anti-commuting relators. It is easy to show that the basis of this algebra consists of ordered products, and then if the length of the product is odd, we say that the element is odd. If it is even, then we say that it is even. So the Grassmann algebra becomes a superalgebra. I should say that again, superalgebras were introduced in 60s, in algebraic late 50s, in algebraic topology under the name graded Lie algebras. Then in 70s, physicists got interested, and because of the connections with supersymmetry, so a more marketable name, superalgebras, got attached to them. It does not mean that they are superior to other algebras. Well, now an important definition. I think it's due to Berezin. Let A be an arbitrary superalgebra. Its Grassmann envelope is this tensor product, this subalgebra of the tensor product of A tensor Grassmann algebra. It's called Grassmann envelope. Now let V be a variety of algebras. What does it mean? It is quite typical to define classes of algebras by identities. You write some identities and you say, let's study all algebras that satisfy these identities. For example, and then that class of algebras is called a variety. For example, associative algebras are those that satisfy the associative identity, so it's a variety. You can discuss commutative algebras, which is a variety. Lie algebras is a variety. So choose your favorite variety. We say that a superalgebra A is a V superalgebra if its Grassmann envelope lies in V. In this way, we have defined Lie superalgebras. So what's a Lie superalgebra? It is a superalgebra whose Grassmann envelope is a Lie algebra. But please remark that a Lie superalgebra is not a Lie algebra. Well, since we know basis in Grassmann algebra, we can take identities that define the variety, substitute elements of the tensor product, expand all brackets, and get a bunch of graded identities, but that would be long. I prefer this definition. In 76, Katz classified all finite dimensional simple Lie algebras. Well, it was a final stroke because it was a long activity with big input from physicists who found many important examples. Okay, now let us talk about the so-called superconformal algebras. You know, the Virasoro algebra plays such an outstanding role in conformal field theory that it was only natural that physicists decided that let us find some super extension of it. What does it mean? Super extension. It means, some super algebra whose even part contains the Virasoro and which did not go far from it. And maybe we could take the models where the Virasoro algebra was so instrumental and instead substitute the super algebras in the model and maybe something good will come out of it. The first attempts were due to Nevier, Schwarz, Ramon, Seiberg, and many other physicists who produced new super extensions of the Virasoro algebra. And these super extensions became known as the superconformal algebras. Katz and van der Leur tried to study that systematically. You know, physicists published papers, this is another superconformal algebra, that's another one. And they noticed that all these examples were graded simple, dimensions were all uniformly bounded from above, and they all contained Virasoro. So they announced a search, classification for all such superconformal algebras, because the situation very much reminds us of this theorem of Katz-Mathieu. In both cases, there are graded simple algebras. In both cases, there are bounds on dimensions of homogeneous components. Maybe a similar classification takes place. So let's consider some examples. Again, we could take a finite dimensional Lie algebra, superalgebra G and take Laurent polynomials over it. All conditions hold except it doesn't contain the Virasoro. Too bad. Another example. This is the analog of the polynomial algebra. Sort of polynomials in one Laurent variable t, which is considered even, and n Grassmann variables xi1, xn, which are considered odd. And we could consider super derivations. You know, in super mathematics, so to say, many usual concepts are superized in the ordinary way. There is a notion of super derivation, a super manifold. So just as a Lie algebra, algebra of derivations of any algebra is a Lie algebra, here we consider super derivations, which is a Lie superalgebra. It is denoted this way. You can consider partial derivatives with respect to these Grassmann variables. And it satisfies all our conditions. Then, considering various differential forms, we can consider analogs of algebras of Cartan type. This is special one. And then the contact one. Okay, another example. If you have an associative commutative superalgebra, you could consider its Poisson bracket. What is a Poisson bracket? First of all, it defines the structure of a Lie superalgebra. And then if you fix one variable with respect to the other one, it's a super derivation. So, if you consider a Poisson bracket on this algebra, it produces a superalgebra of Hamiltonian type. But, for Hamiltonian type, you need two even variables. Here we have only one. So Hamiltonian types do not exist here. but contact type exists. Instead of Poisson algebra, you have to consider some extension of it, contact bracket, which is defined by the second and third conditions. Okay. Here I gave an example of a contact bracket in the super polynomials. Complicated formula, but it exists. So there are some examples. W, special, and contact. And Katz and van der Leur conjectured that these are all superconformal algebras. However, in 1996, independently, Cheng, Katz, and Grossman-Leites-Shepachkina found a new superconformal algebra, which Cheng and Katz have modestly denoted as CK6. As for Grossman-Leites-Shepachkina, since there are many students here, it's a good lesson for you. Cheng and Katz published it in Communications and Mathematical Physics, a very mainstream, very good journal. Grossman-Leites-Shepachkina published it in some Vietnamese journal. They also put it in archive, but in the section of high energy physics. As a result, nobody noticed it. So people started to refer to them only after a certain number of years. So the lesson is publish. In 2001, in a joint paper with Consuelo Martinez, we extended this construction to an arbitrary associative commutative superalgebra and an even derivation, and realized it as an algebra of 8 by 8 matrices over the so-called Weil algebra, the algebra of differential operators. Now, the current conjecture is that it is the old ones and the only new one, CK6. Usually people laugh. That's an easy way to make a new conjecture. But there are good reasons to believe that this new conjecture is correct. Why? Because behind many Lie algebras and Lie superalgebras, there sit Jordan algebras or superalgebras. Many important cases. In the joint paper with Katz and Martinez, we classified all Jordan superalgebras, and indeed it confirmed the conjecture in that case. There is another reason. Katz and Fattori confirmed the conjecture in the so-called conformal case. I will say a few words about this conformal case because it's an amazing story. So what is conformal? In all the superalgebras above, all homogeneous components have the same dimension, say D. So you can choose a basis EI1 up to EID. I is its degree of the component, and D it's basic elements. Now, if you multiply two basic elements, the degrees add, you get I plus J, and again, it becomes a linear combination of basic elements. These basic elements depend on I, J, and P, Q, R. But P, Q, and R run from 1 to D. So there are D cubed functions in two variables, in two integer variables. Now, the conformal assumption is that all these functions are polynomials. You may say that it's a terribly strong assumption. Yes, but it produces all interesting examples. It's like with curves. If you look at algebraic curves, it's a very narrow subclass of all curves, but all interesting curves are there. Different language. Let us write these basic elements as coefficients of some generic function, this function. So what is it? Nothing. It's just a compact, nice way to write all these coefficients. Z is formal variable. It's called formal distributions. Really, formal distributions were introduced by Sobolev and Schwarz. They knew that if Sobolev introduced generalized functions, which later were renamed as distributions, and Schwarz developed a theory of distributions, they knew that if you consider Fourier decomposition of distributions, it is infinite in both directions. So sometimes they are called formal Fourier series. And they knew even this condition. We say that two formal distributions, it is kind of infinite series, which is infinite in both directions, are mutually local if the following formula holds. Now, you see, if you have two formal distributions, you can add them, no problem, but you cannot multiply them. If you multiply two infinite series, which are infinite in both directions, you will end up with coefficients which are infinite sums that do not make sense. So both Sobolev and Schwarz knew this problem. And so instead of this impossible product, they introduced a countable family of possible partial products that altogether approximate the impossible product. This is a partial product. Now, so you change the name of one variable, then the product becomes possible. If two formal distributions are local, then there are only finitely many partial products that are non-zero. Well, and now we can give an abstract definition of a conformal algebra. So what's a conformal algebra? We start with the algebra of coefficients L, and we consider a vector space which consists of formal distributions. And we demand, it's one of our axioms, that any two formal distributions from that space are mutually local, that the space is closed with respect to all partial products, and also with respect to this derivation, because you can differentiate formal distributions. An abstract definition. And it would not be of such an interest if one of these conformal algebras did not have a very interesting group of automorphisms, the so-called monster, the biggest sporadic simple groups. It's an amazing story. In 80s, John Mackay was just looking at various numerology related to the biggest sporadic simple group, and he noticed that the minimal dimension of representation, every finite group can be represented by matrices. The minimal size of matrices needed to represent the monster was a 6-digit number. And he noticed that that number differs only by 1 from certain coefficient of a modular function. That's an amazing observation, because we are talking about 6-digit numbers. It could not be a coincidence. And then Conway, Norton, Thomson formulated a conjecture that the monster has a graded representation such that the graded trace is a modular function, and many modular functions appear in this way. It was such a strange conjecture that it was named the moonshine conjecture. I don't know if you know what's a moonshine. A moonshine is alcohol that you do at home, and it is supposed that if you drink it, that was the attitude to the conjecture. One very famous mathematician on his inaugural lecture at Collège de France mentioned this conjecture, and then he made a bet with his colleague that the conjecture would not be proved or disproved in the 20th century. A box of cognac. The funny thing is that at the time, when the bet was made. The description of this representation already existed in the literature, but in the physics literature. So, that attracted attention to these objects. We say that, since this vector space C is invariant with respect to derivation, we know that if some vector space is invariant with some linear transformation, then it automatically becomes a module of the algebra of polynomials in one variable. So we say that it is of finite type if it is a finitely generated module of this polynomial algebra in one variable. So Katz and Fattori classified all conformal Lie superalgebras of finite type, and it confirmed the conjecture. Now, along with, so this, in a joint paper with Martinez, which is not, hasn't yet been written, it's a preliminary announcement, we confirm the conjecture if the Lie superalgebra contains not the Virasoro, which is ought to contain, but slightly bigger algebra, S12. We need a bit more symmetries. So this is not a final proof of the original conjecture, but very close to it. And the idea is that we define certain formal distributions. We arrange coefficients in such a way that these formal distributions become local, and we get conformal algebra, and we use the existing classification of conformal algebras. By the way, this subject has a reputation of being the subject of conformal and vertex algebras related to them, has a reputation of being unlecturable. Probably all students in mathematics know Gelfand. He had a seminar at Rutgers at the end of his life. And one of the founders of this area gave a talk and gave these definitions. Well, at that time, frankly speaking, the definitions were uglier than this. Gelfand listened and said, I'm more than 80. I have huge experience. I don't understand your definitions. So it means that something is wrong with definitions. Okay, now let's talk about representations of these objects. But what kind of representations? It does not make sense to talk about all representations of infinite dimensional Lie algebras or superalgebras. There are just too many of them. This problem is unmanageable, at least today. So we can talk about, we have to impose some conditions. And the natural conditions are either conformal, as I explained before, or the so-called Harish-Chandra modules. I already basically explained what is conformal. It means that you can arrange coefficients in nice formal distributions such that locality holds, and then you can demand that it is a finite type. What's Harish-Chandra? All superconformal algebras are graded. So we demand that the module is also graded. And all homogeneous components are finite dimensional. That's it. There was an early success. Olivier Mathieu in 1991 classified Harish-Chandra modules over the Virasoro algebra. He proved that all of them are either highest weight modules or lowest weight modules. These are also two very big classes, which, demand further study. But at the first approximation, let us say that this is a classification. Or they are so-called intermediate modules that were introduced by Kaplansky and Sansarubane and independently by Fagin and Fuchs. These intermediate modules, Virasoro is the algebra of derivations of Laurent polynomials. So Laurent polynomials is a natural model over it. And these are some deformations of Laurent polynomials. This is a formula. It is parameterized by two parameters from the field. Recently, Bilic and Futorny classified irreducible Harish-Chandra modules over the n-graded algebras, only this algebra. Okay, now, in the last 25 years, Katz and his students produced big literature on classification of all irreducible conformal modules of finite type. Well, they basically classified all of them, and the last brick was done also in our paper with Martinez. It's another approach. Recently, we classified all Harish-Chandra modules over all superconformal algebras except small types, small cases. You know, when I was at Yale University, Walter Feit of famous Feit-Thompson theorems was kind of my senior colleague, mentor. I remember he saying that the most interesting cases are small cases. So we did all non-small cases. The idea is the same. We reduce Harish-Chandra to conformal. I initially said that there are two interesting types, Harish-Chandra modules or conformal. It turns out that they are the same. Proof locality. Well, I am afraid that I already made you tired with technical details, so probably I should finish. Thank you for your patience.